Good day, viewers. Welcome to another edition of NAMSSN tutorial. So this is MAT 331 complex analysis 1. In our previous video, we stopped at analytic and harmonic function and functions of complex variable. So today we want to talk about the Cauchy theorem and its application. So the theorem goes like this: let f of z be an analytic function within and on region R, then the integral of the function equals to 0. So we know when a function is analytic. So a function is analytic if the function is differentiable at a particular point z0 and is also differentiable at the neighborhood of that z0. So this theorem is talking about when we have a function and then we are integrating around a closed loop like this. Let's say we're having something like this, and then we are, let's say this is a closed loop C. Say this is C, this is Y, and this is X. So if we are integrating, if we are moving along this line, or if we are integrating along this closed loop like this, so the integral is 0. So the integral along the closed loop is 0 according to Cauchy theorem. So let's prove the theorem. We know that f of z equals to u plus iv according to function of complex variable. So where we are going is that if I integrate around a closed circle, or if f of z is u plus iv dz, and we know that if z equals to x plus iy, if we take the partial derivative of both sides, dz will be dx plus I dy. So this dz now we change it to dx plus I dy. So where we are going is that this integral must give me 0. How? Okay, so integral of c, if I open the bracket, this will be u dx plus iu dy plus iv dx. I squared is minus 1, this will be minus v dy. So the next thing is that we separate real and imaginary. So we are going to have integral of this is u dx and this is v dy. We are going to have u dx minus v dy. This is 1 plus the imaginary part. The imaginary part of the integral, the one with I, that will be I, let's say integral around a closed circle. This one will be u dy plus v dx. So this is the second one. And then from here now, what are we going to do is that we are going to recall from Green theorem. Green theorem goes like this. Whenever we are integrating, let's say we are integrating a dx plus b dy, for example. If I'm integrating something like this, it will now be the double integral around the region R of the second part here. They differentiate b partially with respect to y. So we now take the partial derivative of b with respect to the first one, dx, minus, we differentiate the second one, a, they differentiate a with respect to x now. So we now differentiate a with respect to the second variable, dy. So this is dx dy. So we now put dx dy like this. So this is a Green theorem. Whenever we are having something like this, just take the second one, the second variable here, b, we differentiate it partially with respect to the first one, minus, take the first one, differentiate it partially with respect to the other variable, y. So from here now, if I now relate what is here now, everything here, with this green theorem. This is u dx minus v dy. So from here now, we are going to have double integral of region R. The second variable here, this is minus v. The first differentiate it with respect to y. Will now take the partial derivative of v dv with respect to the first one, dx, minus, then we differentiate this first one now with respect to the other variable, du dy along x and y. This is the first part. And then the other part, iu dy plus v dx. So I will be there as the imaginary part. This one will now be double integral of region R. If I take the partial derivative of v with respect to y, minus, we take the partial derivative of u with respect to x along x and along y. So this is interpretation of the green theorem. So from here now, we have minus dv dx du dy. Recall from our Cauchy-Riemann equation. Recall from CR equation. What is CR equation? So the four partial derivative du dx equals to dv dy, and then du dy equals to minus dv dx. So you can go back to our playlist on how we prove all these four partial derivative. So minus dv dx now. Minus dv dx is equals to du dy. So we are going to have a double integral of region R. This minus dv dx is du dy. Then you don't need to change this, du dy dx and dy, plus I double integral of region R. dv dy is equals to du dx. So we just change this dv dy to du dx minus du dx along x and along y. So we observe that du dy minus du dy, that's 0. Everything here is 0. Du dx, everything here is also 0. Therefore, the integral of this function z is 0. So we prove the theorem. So the integral along a closed loop is equals to 0 according to Cauchy. So let's do some application of it. I have about 6 problems here on application of this Cauchy theorem. So you can just pause the video and then go over it again. Example 1. Verify Cauchy theorem. Verify Cauchy theorem by evaluating integral of z square along c dz. Where this c is a square this time around, joining the point z equals to 1, z equals to 2, z equals to 1 plus I, and z equals to 2 plus I. So our endpoint, where are we going? We must get 0. That is our endpoint, because they just want us to use Cauchy theorem to verify. Because according to Cauchy theorem, whenever we are integrating along a closed loop like this, we must get 0. So we want to integrate along all these 4 points. So this particular integral is under line integral. So if I want to integrate z square dz, so the first thing is that let me first sketch all these 4 coordinates. These are the coordinates y and x. So z equals to 1, it means that x is 1, the real part, x is 1. Z equals to 2, it means x is also 2. This is first one, this is the second one. That is there is a line that will go like this, to this end. And then the third one, 1 plus I. Don't forget from our previous video, I said whenever we are having something like 2 minus 3i, it means that x equals to 2, y equals to minus 3 on a rectangular plane. So if I have 1 plus I now, it means that x is 1, y is 1. So this is x is 1, y on imaginary axis. This is 1. This is another one. Z equals to 2 plus I. 2 plus I means that x equals to 2, y equals to 1. That is x equals to 2, y equals to 1, somewhere here, like this. So if I now join everything together, I will have a complete square. So suppose I want to move in, since the question is not specific, I can either move in clockwise or in anti-clockwise direction. So let's say I'm moving like this, then I'll go like this, I'll move like this, and come back like this. So don't forget, the integral around this closed loop is 0. It must give us 0. Okay, so z is x plus iy. This is x plus iy all squared. dz is equals to dx plus I dy. So you expand this, we are going to have x squared plus 2ixy iy. That's minus y squared dx plus I dy. Now let's start from here. We can just label it. Okay, this is point A, point B, point C, and point D. So my first movement, I want to move like this. It means that I want to move from x equals to 1 to x equals to 2. Where I'm coming from will be my lower bound. Where I'm going to will be my upper bound. So here now, if I'm moving like this, it means that I'm moving from x equals to 1 to x equals to 2. So let's say along the line AB, along AB now, it means that we are moving from x equals to 1 to x equals to 2. You know, if I'm going like this, y is constant. It means y is 0. So that is y equals to 0. And if y equals to 0, if I differentiate y equals to 0, my dy will also be 0. So from this my integral now, anywhere I see y, I will change it to 0. Anywhere I see dy, I also put 0. So we are going to have x squared. Since I'm moving like this, y is 0 in that region. So y is 0. This part will not be there. This part will not be there. This part will not be there. So I'm just going to have x squared and dx. So if I integrate x squared, that's s cube over 3 from 1 to 2. Put 2 here, that's 8 over 3. Put 1 here, 1 over 3. That will give us 7 over 3. So let's say 7 over 3 plus 0i. Let's say 7 over 3 because we are doing complex integration. Our solution must be in complex form, real and imaginary parts. So it means that I've moved from here to here. So my next movement is from here to this side, where it means that I'm moving from y equals to 0. Now y is changing. So this is y equals to 0. I'm moving from y equals to 0 to this region to y equals to 1. So let's now say along, this is from here to here, along BC. The integral along BC will now be integral from y equals to 0, because anything like this, y is always 0. From y equals to 0 to this part to y equals to 1. Now, if y equals to 0 and y equals to 1, what is x? So from here now, x is always 2. X is constant. X is 2. So it means that x equals to 2. And if x equals to 2, if I differentiate, the x will be 0, because if I differentiate, the derivative of a constant is 0. So this is the integral we'll be referring to. Let me just start it. So from here now, x equals to 2. Put x equals to 2. 2 raised to power 2, 4. X is 2. 2iy. That will be 4iy. Y will be there. I'll just put y. And if x is 2, dx is 0. Dx is 0. This part is 0. It will remain I dy. So I would just be a constant. It means that we are going to have I integral from 0 to 1. 4 plus 4iy minus y squared dy. So if I integrate 4, so we are going to have I into bracket 4y. If I integrate 4iy, 4iy squared over 2, that's 2iy squared. 2iy squared. If I integrate y squared, that's y raised to power 3 over 3. From where? From 0 to 1. Putting 1 here. If I put 1 here, that's I into bracket 4, put 1 here, that's 2I, put 1 here minus 1 over 3. And if I put 0, since we are dealing with definite integral, put 0, put 0, put 0, everything will be 0. So it won't have any effect. So what is 4 plus 2I minus 1 over 3? Oh, well, 4 minus 1 over 3, that's 11 over 3. This will be I into bracket 11 over 3 plus 2I. Using I to open the bracket, that one will give us 11 over 3I minus 2, because I squared is minus 1. 11 over 3I minus 2. That is when I'm moving like this. So the next one is to move from C to D now. Along CD. Now along CD. So along CD, it means that we are moving from here to here. So that part, that's our integral. This time around, x is changing, y is constant. From here now, x starts from where? This is a region where x is equals to 2. X starts from 2, and s goes to where? To this point. This is 1. So x starts from 2 to s goes to 1. If s starts from 2 and s goes to 1, what is y along this part? Y is always 1. That means y is 1. And if y equals to 1, the y is 0. So substitute into this integral. That's the integral of x squared. Y is 1. If y is 1, this one will be 2ix minus y squared minus 1. 1 squared is 1. Dy is 0 to remain dx. So we are going to have, if I integrate x squared, that's x raised to power 3 over 3, integrate 2x, or that's ix squared, integrate 1, that's x from 2 to 1, or from 2 to 1. If I put 1, we are going to have 1 over 3. If I put 1 in place of x, that's I, put 1 minus 1. Then I will now put 2. Put 2 raised to power 3, 8 over 3. Put 2 here, that's 4I minus 2. So what is 1 over 3 minus 1? 1 over 3 minus 1 is minus 2 over 3 plus I. 8 over 3 minus 2. 8 over 3 minus 2 is this is 3. 8 minus 6, that's 2 over 3. 2 over 3 plus 4I. So that will be minus 2 over 3 plus I minus 2 over 3 minus 4I. So minus 2 over 3 minus 2 over 3, that's minus 4 over 3 minus I plus I minus 4I, that's minus 3I. That is when we are moving along CD. Now coming back to DA now. So viewers, let's keep the results. The first one is 7 over 3. So let me just keep it here. So the first one is 7 over 3. The second solution is 11 over 3I minus 2. The third one is minus 4 over 3 minus 3I. 7 over 3, command 11 over 3I minus 2 minus 4 over 3 minus 3I. Okay, so the next thing is to move from A to A, from D to A now. Okay, along DA. So you can move in any way, you can move in clockwise, it doesn't really matter. So along DA, it means from A to A, y starts from where? We are integrating from y equals to 1 down to this part to y equals to 0. In that case, in this part now, x is 1. No, x is 1. So if x is 1, the x will be 0. So, well, x is 1. If I put 1 here, that's 1 square 1. Put 1 here, this will be 2iy. Put 1, okay, this is minus y squared. The x is 0. This one will remain I dy. So if I take I out as a constant, it will now be I integral from 1 to 0, 1 plus 2iy minus y squared dy. So if I integrate 1, that's y, integrate 2iy, that's y squared, iy squared, integrate y squared, y raised to 3 over 3. Don't forget I is outside, from 1 to 0. So if I put 0 here, everything will be 0. Put 1, that's minus, put 1, this is 1 plus I, put 1, minus 1 over 3. So 1 plus 1 minus 1 over 3 is 2 over 3. So this will be I into bracket 2 over 3, that's minus 2 over 3 plus I. That's minus 2 over 3I minus 1. Minus 2 over 3I minus 1. So we've moved around the closed loop now. So what's now the sum? So if I now add the four solutions together, the first one is 7 over 3. The second one, like this, is 11 over 3I minus 2. The third one is minus 4 over 3 minus 3I. And the last one is minus 2 over 3I minus 1. So 7 over 3 plus 11 over 3, that's this is minus 2, 7 over 3. So the sum, so the sum will now be integral of f of z dz. It will now be 7 over 3 plus 11 over 3I minus 2 minus 4 over 3 minus 3I minus 2 over 3I minus 1. So everything will give us 0. So that is all. We verify that by Cauchy theorem, whenever we are moving around the closed loop, the integral will be 0. So let's check another example that is quite different from this, because in class we didn't do much example. So the next example is this, example 2. Integrate from 1 minus I to 2 plus I of 2x plus IY plus 1 dz along two paths. Part A, along x equals to t plus 1 and y equals to 2t squared minus 1. Part B, along the straight line joining 1 minus I and 2 plus I. Look at this integral that we want to use our Cauchy theorem to solve. So we want to integrate from 1 minus I to 2 plus I. Well, this thing will actually look scary. What is 1 minus I? So, well, from the meaning of 1 minus I is just like having 1 and minus 1, like real and imaginary. X is 1, y is minus 1. The upper bound here, 2 plus I, is just like having x equals to 2, y equals to 1. From 1 to minus 1 and from 2 to 1 over 2x plus iy plus 1 dz. So we know that z equals to what? Z equals to x plus iy. If z equals to x plus iy, dz equals to dx plus I dy. We know that one. So here now, we are integrating from 1 comma minus 1 and to 2 comma 1. 2x plus iy plus 1. Dz is dx plus I dy. So we want to integrate along x equals to t plus 1 and y equals to 2t squared minus 1. You know the meaning of this lower bound is x is 1, y is minus 1. X equals to 2 and y equals to 1. So using this transformation, transformation x equals to t plus 1 and y equals to 2t squared minus 1. Now if I differentiate from here, dx equals to differentiate t, that's dt. Y equals to 2t squared minus 1. dy equals to differentiate 2t squared, that's 4t dt. Okay, now when x is 1, the boundary will also change. When x equals to 1, that's like, okay, when x equals to 1, that's 1 equals to t plus 1, t will be 0. And when x equals to upper bound, when x equals to 2, t will be put 2 here, that's 2 plus 1, so 2 minus 1, t equals to 1. And then when y equals to minus 1 for y, when y equals to minus 1, that's minus 1 equals to 2t squared minus 1. So minus 1 cancel from both sides, t equals to 0. And when y equals to the upper bound, when y equals to 1, when y equals to 1, so 1, take it to this side, as 2 equals to 2t squared, t will be 1. So you observe that when x is equals to 1, when y equals to minus 1, t is 0 for both lower bound. So we are now going to integrate from t start from 0. When x equals to upper bound, t equals to 1. When y equals to 1, t equals to 1, to t equals to 1. Okay, 2x, that's 2 bracket x. What is our x? X is our t plus 1 plus y equals to 2t squared minus 1 plus 1, open bracket, close the bracket, and dx equals to dt, or dy equals to 4t dt, that's I times 4t dt. We are moving from t equals to 0 to t equals to 1. This is 2t plus 2 plus 2it squared minus I plus 1, multiplying by, you can factorize the t, that's 1 plus 4it dt. And then we expand from 0 to 1 over 2t times 1, 2t. 2t times 4it, that's 8it. 2 times 1, that's 2. 2 times 4it, that's 8it. 2it squared times 1, 2it squared. 2it squared times 4i, that's minus 8 t raised power 3, because I squared is minus 1. Minus I times 1 is minus I. Minus I times 4it, that's plus 8it. 1 times 1 is 1. 1 times 4it is 4it. Everything with the t now. So collect like term. So we are moving from 0 to 1. 2t, that's the only t that we have. 2t. 8it plus 8it, that's 16it. 8it plus 8it, that's 16it. 16it plus 8it, that's 24. 24 plus 4, that's 28it. It squared, 2it squared, that's the only 2it squared, and then minus 8t cube, this is 2 plus 1, that's plus 3 dt. So we now integrate. So integrate 2t, that's t squared. Integrate 28it, that's a plus 28it squared over 2, that's 14it squared. Integrate 2it squared, that's 2it cube over 3. Integrate 8c cube. That's t raised power 4 over 4. That's 2t4. Integrate 3. That's 3t. Now from 0 to 1. So if I put 1, we are going to have 1, put 1, 14i, put 1, 2i over 3, put 1, minus 2, put 1, plus 3. And if I put 0, everything will be 0. So on simplifying this, we are going to have 1 minus 2, that's minus 1 plus 3, that's 4. 14 plus 2 over 3. 14 plus 2 over 3. We are going to have 3, 1 in 3, 3 times 14. That's 42 plus 1. That's 43i over 3. So that is when we integrate along x equals to t plus 1 and y equals to 2t squared minus 1. So B part, along the line joining joining 1 minus I and 2 plus I. So what does that mean? This 1 minus I is just like 1 comma minus 1, real and imaginary, and 2 plus I is just like 2 comma 1, real and imaginary. So since they've mentioned line, we need the equation of this line. Okay, let's say 1 comma minus 1, it means that when x equals to 1, y equals to minus 1, let's say that one is around this point. 2 comma 1, that's when x equals to 2. Let's say this is x equals to 2, y equals to plus 1, 1. That one will be around this part. So they are talking about the equation of this line, y and x. So if I find the equation of this line using our normal gradients and intercepts, y minus y1 over x minus x1 equals to y2 minus y1 over x2 minus x1. This is x1 y1, this is x2 y2. So that's y minus minus 1, that's y plus 1, x minus 1. What is y2? y2 is 1 minus y1, that's 2, x2 is 2 minus x1, that's 1. So we are going to have y plus 1 over x minus 1 equals to 2. So y plus 1 equals to 2x minus 2. So y equals to 2x minus 3. So this is where our transformation will now start from. So we want to integrate along this line. We want to integrate along this line 2x minus 3, y equals to 2x minus 3. It means that we are changing y to 2x minus 3. So if y equals to 2x minus 3, dy equals to what? Y equals to 2x minus 3. Now, what is dy? So if I differentiate 2x, that's 2 dx. Then what the interval of y will change to what? When y equals to minus 1. When y equals to minus 1, the lower bound. If I put minus 1 here, we are going to have minus 1 plus 3, that's 2. X will be 1, right? When y equals to the upper bound, when y equals to 1, x will be what? So if I put 1 here, transfer 3, that's 4, x will be 2. It means that this time around we are moving from x start from 1, this is the lower bound, and then to where? To x equals to 2. Of 2x, well, 2x will remain as 2x. Unlike the previous example is that we are transforming x and y at the same time. But this one, we are only changing y to 2x minus 3. So we are going to have 2x plus iy. That's I bracket 2x minus 3 plus 1 dz. What is dz is dx plus I dy. And if y equals to 2x minus 3, dx will remain as dx. Dy is what? Dy is 2 dx. This is I2, or let's say 2i and dx. 2i and dx. So we are moving from 1 to 2 of 2x plus, open the bracket with I, 2ix minus 3i plus 1, right? Factorize dx. This one will be like 1 plus 2i and dx. Okay, so from here now, this 1 plus 2i is a constant. To make the integration easy, 1 plus 2i is a constant. You can just bring them out. So we should become 1 plus 2i integral from 1 to 2 of 2x plus 2ix minus 3I plus 1 dx. So we are having 1 plus 2I. Now if I integrate 2x, that's x squared. Integrate 2ix, that's I x squared. Integrate 3I. So 3I is a constant. That's minus 3ix. Integrate 1. That's x. We are integrating with respect to x. So from 1 to 2, that will be 1 plus 2I. Or put 2. That's 4. Put 2. That's 4I. Put 2 minus 6I. Put 2 plus 2. Then minus. Put 1 here. That's 1. Put 1 here. That's plus I. Put 1 minus 3I plus 1. So factorize the whole thing. We're having 1 plus 2I into brackets. 4 plus 2, that's 6. 4I minus 6I, that's minus 2I. And then minus 1 plus 1 is 2. I minus 3I is minus 2I. So we are going to have 6 minus 2I minus 2 plus 2I. Multiplying 1 plus 2I. So minus 2I plus 2I go. 6 minus 2 is 4. So we are going to have 4 into bracket 1 plus 2I. That's 4 plus 8I. This is the solution when we integrate this function along line 1, minus 1 and 2, 1. Don't forget, whenever you see something like this, just break it into coordinates x and y. 1 and minus I, that's x is 1, y equals to minus 1. 2 plus I, that's x equals to 2, y equals to 1. The basic thing of what we have been doing so far is that Cauchy say that whenever we are integrating, let's say I have something like this. So if I'm integrating around a closed loop like this, from here, let's say from here, go like this, and to here. So the integral, everything will be 0. That was the first example we did. And sometimes they may not ask us to integrate around a closed loop. So they can just ask us to integrate along the line, or they ask us to integrate along 2 points like this. So that is how we apply Cauchy theorem. So our next video, we are going to be talking about residue theorem and its application. So thank you. For correction and criticism, you can drop it under the comment section. Like, share, NAMSSN Unilag. Thank you.